Okay, I'm back, and we want to talk about the history of the universe. And this is a chart that goes through it, and I know that you can't read it, but you can put me on pause and you can expand the picture so that you can read all the wording on there. So there's only one time that I would want you to know about on there, and then you don't need to know about any of the temperatures that are listed on that chart. So the idea is to just know the general steps in the formation of the universe. So we're going to start at the earliest possible time that the laws of physics, as we know them today, still existed. And that is going to be 10 to the negative 43rd seconds. So prior to 10 to the negative 43rd seconds, we don't know what the universe was like. We don't know the temperature of the universe. We don't know the size of the universe. We don't know the forces that controlled the universe. Now, for a lot of us, now remember, this is 10 to the negative 43rd. So this is 0.000000000 43 zeros, 1 seconds after the Big Bang. And we're saying that we don't know what happened before that instant in time. So that means that after this instant of time, up until the present, we can explain how the universe evolved. And that's pretty impressive. But this would be a moment in time that I think that you should know for an exam. So this is, we're going to say that the Big Bang happened, and I'm not even going to say why did the Big Bang happen. So we're just going to say it happened. If you're interested in knowing how it happened or why did it happen, go to the internet and there's all sorts of different theories, but we don't need to go back that far. So let's just assume that the universe begins as an object even smaller than a quark. And it was incredibly hot and it was incredibly dense. So you might be saying, how could the universe begin that small? Well, in general theory of relativity, we say that space and time go together to make space-time. So space is sideways, in and out, up and down, so 3 dimensions, plus the dimension of time is going to make space-time. And so space-time, according to general relativity, can expand. And so we think that the entire universe was compressed to a size smaller than a quark because space and time itself was that small. And then after the Big Bang, it began to expand. Okay, now one of the things that was, one of the first things that happened after the universe began to expand is that the forces began to separate. So today, there are 4 fundamental forces. So that you have gravity, and then there is the strong nuclear, and then you have the weak nuclear, and then you have the electromagnetic. So the electromagnetic force. So those are the 4 forces that control the universe today. Now I'm sure that you're all familiar with gravity. So any 2 objects that have mass, like the mass of this thing and then the mass of the Earth, attract each other because of gravity. The strong nuclear force is the thing that holds the protons and neutrons together inside the nucleus. The weak nuclear force is kind of strange. So it can change a proton into a neutron or change a neutron into a proton. And then the electromagnetic is a combination of electricity and magnetism, and then that's what's going to hold the atom together. Well, uh, after the Big Bang, there was, or one, fundamental force that was controlling the universe. And so we call that one TOE. So TOE, TOE, is called the theory of everything. And it would have been all of these forces put together. But as soon as the universe began to expand, it began to cool off. And as it cooled off, this force could no longer exist. And so then the next thing that happened was that broke into two forces. Now, one of the forces was gravity. But the other force was a combination of these three, which was called GUT, or the Grand Unified Theory. All right, now the universe is still expanding, and so as the universe is expanding, it's going to continue to cool off, and eventually even GUT no longer would be able to operate, and so it broke up into the strong nuclear and then these two. And so these two put together was called the electroweak force, because it was partially electrical and it was partially weak. So this was the electroweak force. And then as the universe continued to expand, eventually these two forces broke apart. So now you've got this. So all of this occurred within something like 10 to the negative 35th seconds after the Big Bang. And so from that point until the present, there's only been 4 fundamental forces that control the universe. So what was the next thing that happened after the Big Bang? Well, just like this previous slide shows, matter began to become more and more organized. So that originally, the kinds of particles that would have existed was matter and antimatter. So what is antimatter? Antimatter is exactly the same as ordinary matter, meaning it's got the same mass, but it has different electrical charge, opposite electrical charge, and it's spinning in the opposite direction. So, for example, the ordinary electron has a negative charge. It has an antimatter particle that goes with it called the positron. So it's exactly the same as the electron, except it's got this positive charge to it. And one of the things about matter and antimatter is that when they go together, they turn into energy. And this goes back to Einstein. Albert Einstein showed that E equals mc squared. So it's one of the most famous equations in all of physics. And so what this means is that mass, m, can be turned into energy, and energy can be turned into mass through the use of this formula. So the universe was so hot right after the Big Bang that it consisted of matter composed of quarks and anti-quarks. And they were constantly interacting with each other, and when they would slam into each other, they would turn into energy. But there was so much energy that it could manufacture quarks and antiquarks, so that the universe consisted of matter and antimatter and energy constantly interchanging with each other. Okay, but the universe is expanding. So as the universe is expanding, the temperature is decreasing. And eventually the temperature got so low that the quarks and antiquarks could go together to turn into energy, but now there's not enough energy to manufacture quarks and antiquarks, so that the universe is becoming dominated by matter. And today there's no antimatter in the universe. Now we can manufacture it, but it doesn't last for very long because it combines with ordinary matter and turns back into energy. So our universe is composed of matter. So now the universe is going to be composed of quarks, very, very hot quarks, and electrons, and other subatomic particles. All right, now it's going to get colder. So as the universe is expanding, the temperature is dropping, and eventually it's going to get to the point at which the quarks are going to start to congregate into protons and neutrons. So if we go back to this picture, a nucleon, a proton or a neutron, is composed of quarks. So we say that this is called quark confinement. The quarks are now confined to be inside of protons and neutrons. So there's no such thing today as free quarks. If a free quark is created, it almost immediately tries to find some other way of neutralizing itself and going back into a nucleus. All right, so now the universe is going to continue to expand, and as it expands, now those protons and neutrons are going to begin to slam into each other to form nucleuses. And the first nucleus to form was helium. So one proton is going to be hydrogen. 2 protons is going to be helium. So as these protons start to smash into each other, it's starting to manufacture the elements in the periodic table of elements. And if the temperature had not continued to decrease, all of the elements in the periodic table would have been manufactured this way. But it turns out that the universe was expanding so fast that really only helium formed, a little bit of lithium. So that's the reason why today the universe consists of, roughly speaking, 75% hydrogen and about 25% helium. So that helium came from the Big Bang. All right, now the next thing that's going to happen, though, is that we've now got these nucleuses, and so now we've got these gigantic clouds of gas that are floating around in the universe. And those clouds of gas, which we're going to call a nebula, begin to collapse because of the force of gravity. And as those clouds begin to collapse, they're going to start to get hotter and hotter and hotter until finally those gases that are inside those nebulas begin to collide, and then we make the first stars. So this would be the birth of the first stars. And these stars came in clusters called globular clusters of millions of stars that were being born at the same time. And then as those clusters of stars began to collide with each other because of gravity, that started to make the first galaxies. And so 14 billion years later, we have our universe that is going to be composed of stars, and then galaxies, and then galaxy clusters, and then superclusters. Okay, let's take a break, and when we come back, we're going to talk about different kinds of stars.